All right. Yes. Yeah, it's up. You can just take it. Yeah, you can just take it. Just keep your books out, books away rather. Okay, so presumably you've all taken the exam. There are still a few people left in the course that haven't taken the exam, so we will go over it after they have had the chance to take the exam. This Friday, I am expected to input grades, midterm grades for well, pretty much everyone. I will input the average of your exam 1 and exam 2 for your midterm grade without any extra credit or anything like that averaged in. You all can know that that's still coming and to be added in. Look, let me say anything about grades. Typically, students in this course do no better than the average of their exam 1 and exam 2 grade, which is one of the reasons why I like to enter it that way in the midterm. So in other words, if you would not be excited to get for your final grade what your average between exam 1 and exam 2 is, then your options are work super hard, change what you are doing, and by the way, do not assume just because you did well on exam 2, you'll do well on exam 3 and 4. Exam 3 and 4 grades always correlate with exam 1 closely. They do not correlate with exam 2. So don't get cocky just because you did well on exam 2. I frankly intentionally give a somewhat easier exam for exam 2 to throw people a lifeline. But exam 3 and 4, frankly, are harder. And there's really no way for me to avoid that. So if you would not like for your final grade in this class, the average of roughly exam 1 and exam 2, you either have to do something very different from what you've been doing, or you can consider pass failing the class so that if you get a D, that's a pass, or you can consider withdrawing with the W. Just, Scout's honor, just that's the way that the numbers work. And as you're going to see today, logic and inductive logic especially is a ton about numbers. So that's where we stand with things. So today we're going to start on chapter 5. And chapter 5, from my point of view, is a ton of fun. And if you are worried that if you feel like, is anything that I'm learning here actually applicable to real life? The answer, of course, is yes. Especially what we're going to teach in this chapter. Statistical reasoning is at the base of a ton of important decisions one might make, from whether or not to purchase insurance to what is worth investing your time into, to frankly gambling. I'm here. Don't tell the administration I am going to teach you how to gamble today. At least, the very basics. And I'm going to be honest with you, I'm actually pretty good at it. So this card is one of my favorite mementos. This card is an invitation to Delta Upsilon's Night on the Duck Pond Texas Hold'em tournament, which was held several years ago here. They invited some of the students and some of the faculty to play Texas Hold'em poker. That night, I beat over 60 students and faculty, including a dozen that brought back in a second time at Texas Hold'em poker. I won the iPad Mini, and I brought it home and gave it to my wife for our 15th wedding anniversary the next day. That's what we call strategic use of inductive reasoning. So look, we're going to teach you how to gamble today, and hopefully you will see how these sorts of thinking and decisions are at the root of a ton of things. And frankly, if all you do with it is win your fantasy football league, I'm okay with that too. Yes, ma'am. There's some truth to that because the psychology of the inexperienced player is more erratic. So it's much harder to know what they're going to do. So to be blunt, I'd much rather go up against completely inexperienced. If I have a choice between really, really good seasoned players and inexperienced players, I'll go up against the inexperienced players. But there is something about it that is a little more dangerous, a little more unpredictable. Because it's not just knowing the numbers. I mean, that's a big part of it, but it's also knowing the psychology of what rational actions you should expect other people to make. But new players don't always know what the rational actions are to take, so they become unpredictable. So they'll go all in on a mediocre hand. You'll fold with a better hand, and you'll be like, "What the? You went all in on a pair of fives, really?" So anyhow, all right, let's talk. So far, the deductive arguments that we've been talking about in class could be described in terms of two kinds of statistical syllogisms. The 100% syllogism, the all members of category X are also members of category Y. Specific item A is a member of category X. Therefore, specific item A is also a member of category Y. An example in English, Fido, all dogs are animals. Fido is a dog. Therefore, with 100% certainty, Fido is an animal. Shocking. We did a college class when we did learn that. And it works also the other way. No, dogs are cats. Fido is a dog. Therefore, with 100% certainty, Fido is not a cat. Or to say it differently, there is 0% probability that Fido is also a cat. So those are two extreme deductive arguments that we've been teaching you the framework of thus far. But the truth of the matter is, there are a ton of important things in life that don't work on this sort of all or nothing basis. A tremendous number of things work on a statistical or probabilistic basis. And if you understand how statistics work, it can be an enormous benefit to you. And if you fail to understand how statistics work, it can be an enormous detriment to you long term. In fact, here's a promissory note. Sometime in the next 2 weeks, I will teach you the statistical formula that maximizes your potential for the best true love marital relationship possible. And by the way, I'm not joking. So you can use statistical reasoning for all sorts of things, including romantic sexual marital relationships. And only a Vulcan like me would dare to tell you. All right, so here is sort of a base model for how probabilistic reasoning works. N% of members of category A are also members of category B. That should be a little x. Little x is a member of category A. Stupid autocorrect. Capitalize it because it was at the front of the sentence. No farther information relevant is available. Therefore, there is an n% chance that little x is also a member of category B. All right, so what does that look like with real life and real reasoning? Looks something like this. My favorite basketball player of all time, Charles Barkley. 80% of Charles Barkley's free throw shots succeed. This is a free throw shot attempt. We have no further information available. Therefore, on this current attempt, we should predict that there is approximately an 80% chance that this free throw opportunity will succeed. So that is how the base probabilistic reasoning from a sample works. There's a bunch of other things that, this is very simplistic. One thing that we should mention, you want a large base number for that first line, n% of A's or B's. So this is why in all sports there are sort of minimum numbers of attempts required. Because otherwise the person who would have like the highest free throw percentage would be like the fourth string basketball player that took 2 free throw shots on the whole season and made them both for a whopping 100%. But we invalidate those. We don't include such low sample sizes in such things because we know they're skewed. They're not an accurate representation of comparative skill. Okay, so now we talk about adjustments. 80% of Barkley's free throw shots succeed. He's about to take a free throw shot. But we have this additional piece of information. Barkley is injured. And since he is injured, or when he's injured, he tends to underperform about 20%. Therefore, there's not an 80% chance of this shot succeeding, but a mere 60%. So, and this, again, if you play fantasy sports, when your players are injured, they tend to do a little worse. When your players are at home, they tend to do a little bit better. There are all sorts of important, interesting correlations that one can identify and predict. And it can work both ways. We might say 80% of Barkley's free throw shots succeed. He's about to step up to the free throw line to take a shot, but Barkley is on fire. I don't know if they still use that expression. We used to say if players on fire, if they were overperforming, if they were doing particularly good, and therefore they were overperforming by 10%. And we would therefore conclude that there's something like a 90% chance that this free throw shot will succeed. So again, there are many ways to make adjustments, and then what is rational to do based on the probability shifts as the adjustments shift the probabilities. All right, let's talk a little bit about reliability. An argument is considered strong and reliable if and only if it is structured in such a way that if the premises are true, then the conclusion is likely to be true. So, you need over 50%, 51%, or if you want to take it out to an extra digit, you say 50.1%, something like that. An argument is weak if and only if it is structured in such a way that if the premises are true, then the conclusion is unlikely to be true, less than 50%. Now note, there is still a role for weak arguments. So for example, in predicting who's going to win the Super Bowl next year, none of the 32 teams will have more than a 50% probability. And sometimes the best you can do is the highest percentage weak arguments one can identify and predict. And then you would want to bet on them. But you would get better odds. All right, so the deductive, inductive language comparison, deductive arguments that are properly structured are valid. And if they also have true premises, they are called sound. Inductive arguments that are properly structured are strong. And if they also have all true premises, they are called reliable. All right, now let's talk about how we calculate odds and probabilities. To calculate the probability of an event, you take the number of favorable cases in a sample size, in a sample, and you divide it by the total number. So if Charles Barkley has attempted 100 free throws, and he has made 75 of them in the past, then you divide 75 by 100, and you will get 0.75 or 75%. And then when he steps up for his 101st attempt, you say he's got approximately a 75% probability that he will make his free throw attempt. So if you want to express it in terms of an odds ratio, the odds in favor of a successful event, you take the number of favorable cases and you divide by the number of unfavorable cases. So for a free throw where he's made 75 and missed 25 and he's taken the next one, you would say the odds are 3-1 in favor of him making the next free throw. And you would say the odds against him, the odds against an unsuccessful free throw would be, you'd take the unfavorable cases and divide by the favorable cases, and you'd say there's a 1 in 3 set of odds against an unsuccessful free throw attempt. So to make a fair bet, if you were betting against Barkley, the person who was you were betting with should give you triple if you're correct and he misses. So these ratios become very important in gambling. Not everything is a 1-to-1 ratio. And even a slight advantage consistently will result in a huge win for the person with the slight advantage. This is why casino gambling is almost always a foolish thing to do, because all of the basic games are rigged against you with slight probability inequities. So if there's a 48% chance you're going to win roulette or blackjack or slot machine, that means that 2% difference will add up enormously over time, and that's how the casinos pay for everything. That's why they always come out ahead. All right. Now let's tie this in a little bit with our previous conversation. We can talk about necessity and contradiction. Remember, we've got things that are analytically true from our previous chapter, and we have things that are self-contradictory. Things that are analytically true is another way of saying that they are necessarily true. They are necessarily true with 100% certainty. And again, a bachelor is an unmarried male 100% of the time. In contrast, if a claim is self-contradictory, that means it is 0% likely. So it is 0% likely that a square can also be a circle. It is 0% likely that a cat is also a dog. It is 0% likely that a Diet Cola can be really good tasting, and so forth. All right, now let's talk about independent variables. The way odds work is something like this. There is sort of a naive way of thinking about statistics that will consistently get you the wrong results. So here's a naive way that a young person might reason about results. Well, gee, if I am going to flip a coin twice, and there's a 50% chance of getting heads on the first one, and a 50% chance of getting heads the second time, then it's like absolutely certain that out of 2 coin flips, I'm going to get heads at least once, right? Now that, of course, is incorrect, and just thinking about it for a second, it shows that it's incorrect, but why is it incorrect? It's incorrect because of this formula. What you have to do is take the probability of event A getting heads the first time, and the probability of event B getting heads the second time, And here is the probability of getting heads twice. You only have a 50% each chance each time, and there's a 25% chance that you would get heads twice. I think the next formula will show why you won't get heads at least once. It's because 1 out of 4 times you're going to get tails twice. All right, well here, this actually is a different formula than I thought it was going to be. This is a formula for events that are mutually exclusive. So this is where we are trying to calculate the probability of event A or the probability of event B when both can't happen. And this is the relevant formula for drawing cards. So if you're playing some sort of cards and you need to draw either an ace or a king to win, your odds of getting what you need are actually 2 in 13 because you'll be 1 in 13 chance, assuming that all the cards are still in the deck, of getting an ace, and a 1 in 13 chance of getting a king. And what makes cards and counting cards difficult is the numbers are constantly shifting because you keep pulling cards out of the deck. And that's actually how card counting works, is you track what cards are still in the deck, and the odds of those cards coming out constantly increases. Very, very hard to do well. All right, if event A and B are not mutually exclusive, then the odds of getting heads at least once on 2 coin flips. All right, this is the thing I referenced before. A naive way of thinking would think, well, gee, it's a near certainty that I would get heads at least once out of 2 flips because you got a 50% chance on each attempt. The way it actually works is probability of event B or A. You take the probability of the first event, the probability of the second event, but then you are forced to subtract the probability of both event A and B occurring. So again, if you talk about this with coin flips, the probability of the first coin flip coming up heads, event A, is 50%. The probability of heads coming up the second time, event B, is 50%. But the reason that doesn't make, isn't a near certainty that you will get heads at least once is because there's a 25% probability of tails coming up twice. So you only have a 75% chance of getting heads at least once in 2 attempts. And again, most uninitiated people make that mistake. I mean, they know that heads doesn't always come up once, at least once out of 2 times, but they think it's like a 90 or 95% probability when it's much less. It's only 75%. All right, but what if the probability of A and B are not independent? And when we're saying that they're not independent, what we're saying is that the success of event A changes the probability of the success of event B. And this happens when drawing cards. So let's say you're in a really bad situation in cards and you need to draw 2 aces out of the 52 card deck to win. Well, this is a really bad situation, but it's even worse than one might calculate because there are 4 aces in the deck. When you draw successfully the first ace, you actually have a substantially worse chance of getting the second ace because now there are only 3 aces in the deck out of 51 cards. So getting an ace on the first draw, there are 4 aces in the deck. There are 52 cards. You have a 1 in 13 chance of getting it, which is about 7.6%, 0.076. But if you successfully get the ace on the first draw, then what's left in the deck is you only have 3 aces and 51 cards left. And if you calculate that out, that comes out to 1 in 17, or a 0.059 chance. Again, it's a 5.9% chance. So you have a substantially worse chance of getting the second ace if you get the first ace. And then you calculate that out, you multiply the two times each other, and you get the odds of getting both aces out of a 52 card deck is only about 1 in 221, or less than 0.5%. So again, our odds get quite a bit worse. But it's important. I mean, look, I don't expect you all to be able to do this sort of math in your head. And even the specifics, I mean, we're going to do the ones on the test are going to be pretty basic things, in my opinion. But it is important for you to know the generalities of how these odds work. That taking out one of the favorable events out of the realm of possibilities substantially lowers your chance of getting the second favorable event. Those are the sorts of things that I hope you will learn from this. All right. Actually, I'm not quite ready for that. Let me reset that slide. And let me find the session number. All right, so this is session number 363-806. All right. So after you've got your response square set up, let's talk about this. We're playing blackjack. You've been dealt an ace, which is a very favorable first card to be dealt. You're going to get a second card, and you want to calculate the odds of getting a card that's worth 10 points. There are four types of cards worth 10 points, and there are 4 of each in a standard single deck. But we are using a double deck with 2 52-card decks of 104 cards. What are the odds of getting a card worth 10 points as your second card? And I should mention, on the test, I will allow you access to a calculator. That being said, I don't actually think access to a calculator helps most people, because what these questions really are asking is not can you do the math, but instead they ask, do you know how to set up the problem? And the calculator won't set it up for you. All right, let's see how we did. All right, we're kind of all over the place, although I am happy to see that the plurality got it right. So the correct answer is 32 in 103. Here is what you're looking for. You are looking for the number of favorable cases over the number of total cases. The total cases here is how many cards are left in the deck. So we told you we're starting with 104 cards, but it didn't stay at 104. Why? Because you've already been dealt an ace. So you have 103 as your denominator. Then we have to figure out how many cards worth 10 points are in the deck. And we start with 4 types. And there are 4 types. There are 4 of each in the basic standard deck. But we're using a double deck, so we have to double that number. So it's 4 types, tens, jacks, queens, kings. There's 4 of each suit, diamonds, clubs, spades, and hearts. And then we have to double it because we're using a double deck. And you get 32, which 42% of you got correct. And again, if you got that wrong because you don't play blackjack, don't worry. But now we're, sort of training you in the ways of thinking relevant to this sort of problem. All right, maybe you don't like cards. Maybe you like baseball. One of the most notoriously unlucky teams in baseball is the Chicago Cubs. Let's say we calculate that there's a 60% chance of rain today, and that if it rains, the game will be rained out. They won't get to play at all. But if it doesn't rain, there will be a 20% chance that the Cubs will beat the Mets today. So what are the chances, taking both these factors into account, that the Cubs are going to beat the Mets today? All right, let's see. All right, not bad. It's like the majority got it right. All right, this is a 2-step math problem. Step 1, we have to figure out how likely it is that the game happens at all. And that's actually pretty easy. We take 100% and we subtract the 60% chance that the game is going to be rained out. So there's a 40% chance that the game is going to happen today. Then, if the game is actually played, we have to multiply times point, really just by 0.2 for the 20% chance that the Cubs will be successful. And we get a whopping 8% chance that the Cubs will win today. This is why, at least it used to be very bad to be a Cubs fan. But they won the World Series a few years back, so that curse has been broken. But Gensler's probably still a little sore about it. All right, let's try another one. You have tossed a typical coin 5 times, and surprisingly, it has come up heads every time. Assuming it's a standard fair coin and not like a double-sided coin or something, what are the odds that the coin is going to come up heads the next time you throw it, the 6th time? All right, good for you. This is one that I encourage you to underline and star because I always ask something like this on the test. This is called a series of various independent events. Or to say it differently, the coin doesn't care how many times it's come up heads before. Each coin flip is an independent event. Again, assuming it's not a double-sided coin or a weighted coin or something. So the fact that it's come up heads 5 times in a row, nobody cares. So this is sometimes called the gambler's fallacy or the Monte Carlo fallacy, when a gambler thinks, well, this time it has to come up tails. No, it doesn't. The way this works at the casino is if somebody says, I've been sitting here by the roulette wheel betting on number 5 black, number 5 red, I don't know which are black and which are red. But if you keep betting the same number, since each roulette wheel spin is independent, there's no such thing as it's due. It's not due. In contrast, if you're playing a game of cards and you're using the same deck, the deck's getting smaller and smaller, no aces come up. That is a dependent event. And each time a card is dealt and it's not an ace, it makes the next card more likely to be an ace. Which is why card counting, if you're really good at it, can work. But there's no such thing as like roulette wheel counting. It doesn't work. Except maybe in like a James Bond movie or something. All right, now here's the harder one. You have 6 coins and you are about to toss them all. What are the odds that all 6 of them come up as heads? This is the question that many people mistakenly think I'm asking in the previous question. All right, well, here is what we have to calculate. There are 6 coins. Each coin independently has a 50% chance of coming up as heads. So the odds of all 6 of them coming up as heads is 1 in 2 to the 6th. Or to write it differently, 1/2, which is 50%, by 1/2, which is 50%, by 1/2, by 1/2, by 1/2, by 1/2, 6 times. 1, 2, 3, 4, 5, 6. And the correct answer is 2 and 2 is 4, 4 and 2 is 8, 8 and 2 is 16, 16 and 2 is 32, 32 and 2 is 64. So your odds of all 6 of them coming up as heads is a measly 1 in 64 or less than 2%. See how much harder that gets? All right. Questions about any of this? Any of the general principles? Or if there's any of the particular homework problems that you'd like to see me discuss. Yes. Number 12. All right. you're at a casino, $1 slot machine for $2,000. Assume that it's the only way you can win and that it gives mathematically fair odds or worse. Huh. Well, if it gave mathematically fair odds, it would be a 1 in 2,000 chance. But I don't know what to do with the or worse. That's a very oddly phrased question. Did anybody come up with anything more insightful than 1 in 2,000 for that? Good. Yes, that is correct. It would be less than or equal to 1 in 2,000. That is the right way to do that. But yeah, that's not all that interesting, to be honest. But it's a weird way to frame it. Yes?
You do number 10.
Number 10. Your sister's throwing a pair of dice, and she says, I bet I'll throw a number divisible by 3. What is the mathematically fair betting odds? All right, now this one, now I'm assuming we're talking about a pair of D6 dice. So what we need to do is come up with the number of favorable cases on 2 dice over the number of total cases on two dice. Since they're 6-sided dice, you multiply 6 times 2, figure out the number of total cases, which is 36. But the number of favorable cases is the tricky part. Now, the easiest way to do this one is to make yourself a visual chart. That looks like this. So this is the number you got on the first die, this is the number you got on the second die. And actually, there are tables one can memorize of statistics on the odds of what comes up with 2 6-sided dice, because some people have spent a lot of time at Vegas and tried to memorize such things. The number that comes up most frequently is 7 on 2 6-sided dice. All right, now what did she say? It was an odd? An even, okay. So so all you have to do is make this chart, and then you circle all the even numbers. Oh, divisible by 3.
Yeah.
Well, that's a pain. All right, so we've got 2 on the first line, 2 on the second line, 2 on the third line, 2 on the fourth line, 2 on the fifth line, and 2 on the sixth line. All right, so that's 2, 4, 6, 8, 10, 12. So you have 12 favorable cases out of 36 possible cases, 1 in 3, or it ought to pay out 3 to 1. So how are we doing on this? How's this feel? Now, this is the part where, if you're good at math, I mean, this is what, like 9th grade math, 8th grade math? I mean, this isn't super difficult math. What's difficult is figuring out how to set it up. So this is the part that people who do applied math are really good at. So the physics students is like sitting in the back row of seats at this point, because this is like way, way easier than applied math and physics. But people who aren't used to, aren't good at STEM style calculations are struggling. All right, well, we will continue with inductive reasoning with the next class on Friday. Thank you very much.